Okay, so I guess everything else that you haven't gotten around to giving is due today, except the final, which is next week. And I am going to complete the discussion on LDA today with some discussion on the inference and a couple of other issues, option issues. Okay. Before I start, are there questions?
What will be the pattern of the paper?
It will be sort of similar to the midterm, but I think the focus will be more on the second half. Okay. I mean, to the extent I ask the first half questions, they would be related to the second half discussions. Okay. So the focus is mostly on what we did after the first midterm. Okay.
Any questions in the first part?
What? They can be in as much as I can make them be connected to this. Okay. So I would basically, I think if you just focus on the lectures that happened after the first midterm, that you should be completely fine. Okay. Yeah.
Are you giving us the solutions to the homework?
What?
Are you giving us the solutions to the homework that we just turned in as well?
I can try to have that. Any other questions? Okay. So a bunch of interesting things about the topic models, and we'll end. And I guess the main part of what I'm hoping to do today is walk you through the Gibbs sampling, which you already used. You may or may not have understood why it made sense and what it's doing because you have a tool, but I'm sort of trying to walk you through it. And then time permitting, I might also do something about some work that we've been doing, which sort of can be brought in as a way of generalizing LDA models in many, many different ways. In fact, one of the interesting things about generative models is, as I said, I told you, generative model is a story, okay? And generative models can be put together to make bigger stories, okay? I mean, it's almost and even though I'm making an obviously, common sense metaphor, people do combine stories. I mean, those of you who know any of the epics, okay, and I know half of you from India and you know Mahabharata and the rest of you would know Bible, the stories will be connected into stories and you like a bigger story. And similarly, LDA models, even though we mostly looked at it for the unigram text, they have been extended to do all sorts of crazy things, okay? And instead of just saying that can be done, I might tell you a specific thing that one of my students has done here, depending on the time that's left. Okay. So anyway, continuing to the LDA model. So this is your LDA model, and one thing I want you to look at now, since we are getting ready to start thinking about. Actually, let me wait. Before I do this, let me show this to you, which is that this is a. One more thing. I sent you guys a mail. I know that there have been several different papers on LDA, and it's partly because there is no textbook level description that I could have used directly here. I wanted you to know about unigram model, the single topic model, as well as LDA, and I wanted you to know it at the level that I decided. And then every textbook uses, its own way of writing. And in fact, only Kevin Murphy's textbook actually has LDA written as a textbook format, but the rest are all papers. And papers are always a snapshot of what they did on that particular paper. But I think right now I've reached a local minimum, especially because the semester is ending. I had to pick one, and if I had to pick one that I want you to read, actually in preparation for the final, it's this. I just sent you guys a mail on this. It's basically by Stivers and Griffiths, probabilistic topic models. They wrote this as a chapter in a book on latent semantic models of language. Okay, first of all, it's very easy to read, and secondly, it makes lots of points that you may have wondered, in particular about the LDA model and its connection to other things. Okay, so certainly read this, and in fact, I'm actually going to use a couple of slides from that paper too. This one is actually directly from that paper, so that's a very useful thing to keep in mind. But anyway, read this, okay? I mean, if you haven't read anything else, read this. If you read everything else, this will just be a very quick review, okay? So the thing that I want you to see in this is this idea that now, what exactly is LDA doing in terms of essentially the probability distributions. Okay, we know that topics are distributions. Topics are distributions over words. Okay, and we know that documents are also distributions over words. But you write their distribution over words as first documents as distribution over topics and topics as distribution over words. So the interesting thing is, suppose you have just 3 words in your vocabulary, then essentially you have a 3-dimensional space. Imagine there are only 3 words. In fact, you normally have a million words, so you are talking about a million-dimensional space. So I don't know how to write that. So you have a 3-dimensional space. Okay. Now every possible distribution over these 3 words can be written as a vector in this simplex, right? Every possible distribution. So what that means is both topics and documents are points on this simplex, right? Both topics and documents are points on this simplex. The interesting question is, so first of all, if I didn't tell you anything about topics, the documents can be any point on this simplex. In what sense am I restricting the documents when I say that thou shalt be generated only from a certain set of topics, a mixture of certain set of topics? To get that into mind, think of just 2 topics. In this scenario, let's assume 2 topics. Okay, here are these 2 topics. I've decided this is one topic, this is another topic. Do you see what I'm saying? Okay, now what is interesting is that every document now is going to be essentially, since there are only 2 topics, it would be a convex combination of these 2 topics. Right? Because essentially if I give you 0.3 of topic 1, 0.7 of topic 2, that's a convex combination. So where will the documents live? If you are generating just 2 topic based documents, they will all live on this line. Do you understand what I'm saying? So by deciding that there are only 2 topics, okay, you have said, although documents live in this entire simplex, they don't really get to live anywhere on this simplex. They only get to live on the subspace of this simplex, which is defined by the convex combination of the topics. Do you see what I'm saying? So this is the picture that the JMLR paper was trying to write here. I don't know if you can see this, where they tried to write there is a simplex for the words and there's a smaller simplex for the document, for the topics, and the documents are points in the topic simplex. Okay, but the problem is this is hard to understand, to some extent. Well, actually, it can be. You can think of that. The convex combination over these 3 points will be in this particular simplex. Anyway, that's also true. Okay, but here actually it's a nicer example where you can see that all the documents in terms of these 2 topics must live only on this line. That's a generative example. Now suppose what you actually tend to do is you actually observe some documents in the wild. Okay, so these white guys, they're all documents you observed in the wild. Now you're trying to fit 2 topic model to these white guys. This looks like what? It looks like a line fitting. Do you see what I'm saying? It's just a line fitting. So I could have fit a 2 topic model, I could have fit a 2 topic model which is sort of like this, and that wouldn't have been a good fit. Because this model will be generating documents like this, but the documents are like this mostly. Do you see what I'm saying? What?
When you draw a line, what does it mean?
No, that's what I was doing when you were reading your tablet. The 2 topics here, this is topic 1, this is topic 2, and every document is a mixture over topics. And so let's say this document here is 0.3 of topic 1 and 0.7 of topic 2. So every document that can be generated as mixture of topics would be on this line. Do you see what I'm saying? So you are fitting, in this example, you're just fitting a line, okay? But in another example, let's say here, if you have 3-topic model, you're looking for the nicest triangle that actually, captures the entire set of observed documents. And 15 topics, don't ask me what to do because I have no idea how to visualize it. Okay, so but that's basically what's going on. That's a nice intuition to have. It's a nice geometric intuition about what topic models are doing, and that sort of brings them in line with lots of other ideas of dimensionality reduction, such as latent semantic indexing. Okay, that's the useful thing to keep in mind here. Are there any questions here? So this one has both the part that when you have topic mixture, right? I mean, it must have crossed your mind, exactly. Documents are already vectors in the word space. Topics are also vectors in the word space. Why must I think of documents as vectors in the topic space, which are then vectors in the word space? Okay, well, in so doing, you're restricting the kinds of documents that can be generated. Even though there are infinite topic mixes here over 2 topics, it turns out all of them will live on this line. That's interesting. You still are not couching. It's not like every random top generate. No, if you only have these 2 topics, you will not be able to generate, a document that's here. You will never be able to generate it. And conversely, if you mostly are observing documents here, you have no business finding these 2 as the topics. Okay, fine. So the other thing that I'm going to do today is basically this inference aspect. To get there, let's start thinking in terms of the joint distribution that's given by the plate model here. Okay, so in particular, if you have your the LDA here, so you are interested sort of, capturing what's the word. This is one distribution you're interested in capturing, which is what is the distribution of words given alpha and beta. Okay, because alpha and beta are the only this alpha and this beta we're talking about. Okay, now that can be essentially written as this formula here, where there's an integration instead of summation, because theta is a continuous variable. Okay, so what you're doing is you're basically looking at the model and you're realizing to compute the word probability given alpha beta, you're essentially talking about theta given alpha, which you have okay, and then you are basically, once you have theta value and you have once you have a theta value, then you can get z given theta. Okay, and then once you have z, then you get the word given z and beta, and then basically z and beta will be able to tell you the words distribution given the topic, because z is nothing but an indicator variable into the beta matrix. Okay, so that's it. And then the only interesting thing that may be worth looking at here is that there is a summation here. And the summation is because a word could have been generated because of different topics. The same word could have been generated because of different topics. In fact, one of the interesting things in this book is, in this little paper, is it looks at it much more from the language point of view and realizes that when a word occurs in multiple topics, in some sense, that might be capturing what's called polysemy. Okay, for example, the word bank can occur in a river topic and in a financial topic. Okay, and in English, bank has two very different meanings. In fact, many different meanings probably, but certainly has two different meanings. River bank and financial institution, the bank. And that sort of, when a word occurs in different documents with high frequency, it could actually capture the polysemy of that word. Okay, which is one of the interesting things that people are always interested in doing with respect to statistical modeling of language. Can you capture the multiple meanings of the word? Okay, so now in terms of the generation, the word could have been generated either from, so the word bank here could have been generated either from the river topic or the finance topic. And this is basically the marginalized probability of the word given alpha and beta. Okay, by the way, this is just the marginalized probability, and so of course I can also compute the marginalized probability of document given alpha and beta, where document is nothing but a set of words, okay, and you just multiply the word probabilities. Okay, and in doing this, we essentially use the Bayes network topology. Okay, so we start from there. Next thing in general, basically, is we are interested in doing in inference, what we're interested in doing is given these guys, given the white observed documents, you're trying to find the topics that would work as the latent topics. And then find, word distribution over those topics. Okay, that's what you're trying to do. Okay, so I'm basically, and from a graphical model point of view, what you're essentially having here is you have this model, and then all you are observing is the words, and alpha and eta are given. Everything else is actually hidden. Okay, because alpha and eta are given, theta and beta, prior distributions of theta and beta are known, because you just sample it from the Dirichlet prior. Okay, what you really would like to know from a Bayesian perspective is the posterior distribution. But before that, so if I have this model and I give you a whole bunch of documents, D1, D2, etc. up to dk with all their words, okay, and I'm trying to compute the parameters for this network, there are obviously, we got all interested about Bayesian estimation, but obviously there is MLE and map estimation that's possible. In fact, it's not like it's a totally dead idea. One of the interesting things is LDA is but a small increment over a previous idea called PLSA, which is probabilistic latent semantic indexing, latent semantic analysis, which itself tries to provide probabilistic semantics to a matrix factorization idea called latent semantic analysis. And LSA itself is nothing but if you ever took linear algebra, singular value decomposition. Okay, so that's and then from there you come to LDA. And so, in fact, LDA the only difference between PLSA and LDA really from the point of view of the graphical model is that you are modeling the priors. Okay, because you are modeling the priors, typically the minimum you want to do is the map estimation. Not all priors are, not all initial values are equally likely. Okay, if it's not a uniform prior, if you remember, go back to the beginnings of Bayesian learning where we essentially were trying to maximize this expression, and then we said, well, rather than compute the sum, we'll just pick the one hypothesis with respect to which this, with respect to which the factor corresponding to that hypothesis would be the largest in the sum. Okay, and if you do that, that's map. And in the map case, that piece contains both the likelihood of the data given the hypothesis and the likelihood of the hypothesis. And if all the hypotheses are equally likely, then you ignore the likelihood of the hypothesis, and it becomes MLE. Since we actually have priors, okay, since I actually have priors, you have you at least would do a map. Okay, and the map estimation would look very much like MLE estimation. Okay, that's one way of fitting the model. The other is don't fit the model, just compute the posterior distribution given the data, which is what Bayesian learning does. Again, Bayesian learning doesn't actually learn anything, it just tries to compute the posterior. So to get this in perspective, you're trying to compute, the interesting things in this picture are what? Theta and beta. Those are the ones that you really would like to know. Theta tells you what? Theta tells you the topic distribution over documents. For a given document, what's the mixture of topics? And beta tells you what is the word distribution of the topics. Okay, now clearly for both of them, you know in the beginning the prior probability of a particular topic distribution and prior probability of a particular topic, prior probability of a particular document topic mixture, and similarly the prior probability of a word topic distribution are both given because you have Dirichlet priors. Okay, so you know P theta and P beta. Okay, what you would like to do is, have you changed your mind having seen the data? Okay, this prior is when you haven't even seen the data. Now what you want to know is you have seen the words and documents. So what's your posterior probability on theta and beta? That's your best guess. So basically it's like you're trying to solve a case, you already have a prejudged, preconceived notions as to who may have done it. And then as the data comes in, you'll say, well, this hypothesis is more likely, this is less likely. That's exactly what happens in the Bayesian learning. Remember, there was, the 5 hypotheses for the candy. You draw how their likelihood changes as you keep seeing data. That's exactly what happens. And what is interesting is, at the final level, after seeing all the data, what's your probabilities for each of the hypotheses? Those are basically like theta and beta. What's your probability of topic mixture? What's the probability of the topic mixture? What's the topic mixtures and what are the word distributions like, having seen the words that you have in front of you? That's what you're trying to compute. Okay, that's what basically will tell you what are the hidden topics, and for each document what are the topic mixtures. And that's what basically was being shown in that NIPS example I showed you, for example, in the last class. So when they fit, and that's what I assume you found in the project you did for your little data, right? Okay, so you want to compute the posteriors basically, and you just basically use Bayesian updating to compute this. That's all you do. Okay, so there are 2 ways of doing this. Of course, it is Bayesian updating, but except there are complex probabilities, joint probabilities that you are working with. So there are 2 general approaches that have been used, and it's generally true for pretty much any graphical model Bayesian learning, but it's also true for LDA. One is deterministic approximation algorithms. Exact inference is basically out of the question for this, it turns out. Okay, partly because of the continuous quantities. But in terms of the approximate algorithms, there are ideas like variational inference and expectation propagation, which I won't get into. But essentially, you can think of a variational inference as trying to look for a simpler distribution. A distribution from a simpler distribution family that comes closest to as yet unseen posterior. Okay, I don't know whether that made sense to you or not. So this basically, given the posterior, suppose I told you this is how the posterior looks. Okay, and then I said, okay, I can give you, basically you get to fit to this a mixture of 2 Gaussians. So you can play with the family of mixture of 2 Gaussians. So find the 2 Gaussians that will fit this distribution at best. Well, maybe I might just decide to say, well, I'll kind of use a distribution like there, and then another distribution like there. When you add up, it won't exactly look like this red one, but it might look somewhat close. And variational inference winds up being an optimization problem because you're essentially finding the particular set of two Gaussians, which will then define a unique distribution whose distance from the known this red distribution is the lowest. And the distance would be computed as using like distributional distance measures such as KL divergence, which we haven't talked about here, but for those of you who heard of it, you would do that. Okay, now the interesting thing, of course, is if I tell you this, then approximating it is what I've described just now. But the interesting part is that I will never tell you what the red one looks like. You can only kind of get piecemeal information about the red one. And you're trying to find the two blue ones that will correspond to the unseen red one, which is the interesting part about variational inference. Okay, that's what they tried to explain in the JMLR paper, to the extent you got it. Okay, the other one, much simpler one, I mean, this is actually a deterministic one. So this is like, I have decided that I am biased to believe that whatever is my posterior can be expressed as, you know, as a member of this particular family of distributions. Okay, and then I'm just going to find the best one that fits. That's more or less what happens in curve fitting also, right? I mean, I have some random points. They are defining some arbitrary curve. And I'm trying to find the best straight line that comes closest to this curve without having seen the real curve. I only saw points from that curve. Okay? So variation inference looks a lot like optimization problem, which it is, because it's optimizing over the candidates from a simpler distribution, which come closest to this unseen posterior distribution. Okay, that's one idea. The other idea is Markov chain Monte Carlo, and in fact, if nothing else works, you always try Markov chain Monte Carlo, because that's an approximate, sampling-based approximate method. And the interesting thing is that hopefully we'll get to see that even in MCMC, there are good ways of doing MCMC and bad ways of doing MCMC. Okay, so basically Markov chain Monte Carlo, especially with the Gibbs sampling, okay, and I guess I did not complete this sentence. What it tries to do, interestingly, is basically you're going to try and compute the posterior distribution. For example, what you're interested in is the posterior distribution of P theta given WD and P beta given WD, right? And then you can compute that using Markov chain Monte Carlo. We talked about doing that using conditional distributions. Okay, so the only thing that we'll see is upfront we would like to do the MCMC on this network, which is actually quite easy to understand. But it turns out that the sampling approach that you get will be very inefficient because it also samples theta, which is a continuous quantity. And it basically converges slow. And the sampling approach being slow means what? If you remember, what is MCMC supposed to do? Again, let me show you the picture of an MCMC before we go forward. I don't even know whether I have it here. Oh, okay, I don't have this here. Where did my picture go? Oh, there. This is your MCMC picture. We've seen this at least once, if not more times. Okay. So what we are doing here essentially is we were given evidence, sprinkler and wet grass, and I'm basically perhaps trying to compute some other conditional distribution. So, for example, what's the probability of cloudy given sprinkler and wet grass? That's what I'm trying to compute. Okay. To do that, what I did was essentially I tried to think of a Markov chain in the space of complete configurations of this network. Okay, so here is one complete configuration. Remember that in every complete configuration, the evidence nodes will always have their same value. A different complete configuration would basically will still have sprinkler, evidence, wet grass, evidence. Cloudy now this time might be true and rain might be false. The other time rain might be true, cloudy might be false. So the question, of course, is you want to think of basically you are visualizing a Markov chain which sort of goes from one complete configuration to next complete configuration to next complete configuration. There are thankfully only a finite number of these, for this case at least, there are only a finite number of configurations. Okay, and essentially if you can figure out the Markov chain for that configuration, and if you can figure out the steady state distribution of that Markov chain, from the steady state distribution, then you can sample from there what are the more basically if you sample from the steady state distribution, let's say 100 samples, then you can basically say in those 100 samples, cloudy is true in 50 of them. Remember, in all these 100 samples, the evidence is the way the evidence is. Cloudy is true in 50 of them. So that means when these two are true, the probability of cloudy being true is 0.5 by estimate. And the steps in it, of course, are essentially simulating the Markov chain until it reaches steady state. To simulate the Markov chain, the thing we had to remember, this is useful stuff to know because that's how you connect it to what you're doing in the other place. You need, if you basically sample one node at a time. Okay, let's say you are sampling cloudy. Okay, if you're sampling cloudy, the Gibbs sampling essentially is sample cloudy given everything else in their current valuation. So you start by just initializing the node to some values, initializing the network to some values, and then you're going to resample cloudy given everything else. Now that's what Gibbs sampling says. Just resample one node given everything else, one network node given the rest of the network. But since you know you are using Bayes networks of graphical models, the entire network's effect on a particular node is filtered through what? The Markov blanket. So you just basically wind up computing the distribution of that node given its Markov blanket. And then compute the distribution and basically sample that distribution to get the new value. And then do this again and again and again. That's exactly what Markov chain Monte Carlo is. So keep this in mind. That's what we want to do for our example too, for LDA. Instead of this as the network, LDA network would look like that. Okay, basically, this is what you're thinking is LDA network, but really this is the full Bayes network that you have. This is just a shorthand notation. So if you had 3 documents with 4 words each, the entire network would have looked something like this. Okay, of these, the evidence, of course, are the words. The evidence, of course, are the words. So then I'm going to wind up, and I'm trying to compute p theta given words and p beta given words. Right? The way you could do it is essentially the same Markov chain Monte Carlo idea, where you will essentially, you cannot change these guys. This is the entire network right now. This is the state of the entire network. In your Markov chain, each node in the Markov chain would be this entire configuration. The next node would be a different configuration. Now, how do things change from one configuration to another? These guys can't change. The only way you change is the z's will be resampled. So you start this network off by saying, okay, I'll just assume, theta is a particular sample from alpha. Okay, and similarly, beta is a particular sample from beta, which is not shown. And I'll just assume that Z1 is 1, Z2 is 2, if I have 4 topics. Okay, let's see. I didn't tell you how many topics. I did not tell you how many topics here, but assume, let's say, 4 topics. Then I would have used 4 topics. Z1 can be 1 to 4, Z2 can be 1 to 4, and so on. You pick one value for each of these. Now, given this, now I'm going to resample each one of these Z's. Pick a Z, resample it given everybody else in the network. Everybody else in the network. The interesting thing is, if you want to resample this, let's say Z1, given everybody else in the network, what is this guy's Markov blanket? There is a Markov blanket here too, right? Underneath it all, it's an LDA is a Bayes network. So nice thing is that the Z1's Markov blanket, what is the Markov blanket? It's the parents the children and the other parents of your children. Okay, so for Z1, who is the parent? Theta. Who are the children? Just W1. Who are the other parents of W1? Beta. Right? You did not have to deal with any of the other Zi's. And so you just compute that particular posterior distribution using Bayes' rule. And having computed this, so that distribution would probably say that with 0.3 probability, given the rest of the guys' values that they have, with 0.3 probability, oh, by the way, yeah, so with 0.3 probability, Z1 is 1, 0.2 it's 2, and 0.4 it is 3, and 0.1 it is 4, let's say. Now you sample that distribution to get the new value for Z. You put that in. You now have an entirely new copy of the network. Entirely new copy of the network. Now you basically pick some random node from that network, resample it. You keep doing this until you think that the network has stabilized. Okay, this is from Markov chain. If you know anything about Markov chains, the Markov chains basically, under certain conditions, first of all, they have a stable distribution. And for us, the conditions are that there are no deterministic probabilities anywhere. There's no deterministic relations anywhere. Because if there are deterministic relations, then you cannot go from one configuration to another configuration. There at least exist two configurations that are kind of disconnected. If they're all connected, then Markov chain will have a steady-state distribution. Okay, and that steady-state distribution, however, it might be very quick. You might be able to get there very quickly, or you might wind up taking a lot of time to get there. Okay, that's basically this idea of mixing time of the chain. One reason people basically say that this idea that I have in front of me, which is essentially sample in this network, is bad, is because the mixing time for such a network is going to be very, very high. And partly it's because you are sampling theta. Okay. So there is an idea. In fact, this idea is much simpler to understand. And actually, if you go back to this, the full Gibbs sampler. This is called the full Gibbs sampler on the LDA network, and it basically directly samples on this entire network. The other idea is to try not to sample theta. Where what I would say is, why don't I compile away theta? Why don't I just compile theta out? Okay, how do I compile theta out? Well, I can compile theta out if I just remove theta and put links from alpha to all the z's. In some sense, okay? So, in essence, the point I was hoping somebody will say is this just runs completely counter to everything we talked about as to what a good Bayes network is. A good Bayes network puts made up interior nodes to increase the sparsity of edges. And yet I am saying when push comes to shove, I would rather just get rid of some of this structure so that I don't have to touch the continuous variable. That's the most interesting part. So collapsed Gibbs sampling essentially integrates out theta. You can always remove a particular variable from consideration by marginalizing over it, which is basically why I think there is this statement saying the Bayesians are the only ones who feel marginalized when they are integrated. Anyway, if you like it. Okay. So you would basically integrate theta out. Okay, and then in essence you will have a network which won't have theta. But the interesting question is, what would the structure of that network look like? It won't be sparse. Okay? In fact, what would happen is that all the Zi's get correlated. all the zi's get correlated. Okay, and furthermore, not only will they get correlated, if you want to represent them in a graphical model, the correlations between them are representable only by undirected edges. So that part of the network is actually a Markov network, and the rest is still a Bayes network. Okay, so underneath the hood, the beautiful point is that, so these are the 2 points. I mean, this one I'm just going to skip over mostly, that you can essentially integrate over theta and phi, okay, which is the topic mixture and the word mixtures, topic document mixture and the word topic mixtures. The proportions, you can integrate them over, okay. Once you integrate them over, it turns out that those integrals actually can be evaluated, and they're called Dirichlet integrals, and their integral values would be, basically the problem is that, so you have the PZ and PWZ, and in general then what you really want to compute then is, now remember that what I really wanted was theta given everything and beta given everything. Theta given the words and beta given the words. The ones that I want, I integrated them out. They're no longer there. So the only thing I would actually have is z given w's. That's what I can compute now. Now the interesting thing is, once you get the z given w's, you can invert them back to theta given w's. Okay, it's like I somehow ignored this problem for a while, the theta and beta problems for a while, so that I can focus on the z's and w's directly. And then I compute the posterior of z given w. That's what collapsed Gibbs sampling does. And having computed that, you can always re-estimate from the final posterior distribution of z and z given w. You can estimate theta and beta. So that then they come back. That's like a 2-step process. First you eliminate what you really wanted, and then you bring them back after you compute the. That's the interesting part of what's going on here. Okay. So anyway, so in fact, one of the this thing is from this thing is from the paper. I believe I forgot the name. It's the thicker paper which talks about deriving parametric models for language. Okay, which I mentioned earlier, which I sent earlier, and I'm going to show that again in a minute. But they essentially point out that the posterior, given these two, which actually are in closed form, you can compute z given w, except z given w is now intractable. And so you try to estimate z given w using Markov chain Monte Carlo. Okay. Now, one other thing I want you to see is that, okay, unfortunately, this picture is a nice picture from Kevin Murphy's book, except, as I said, everybody uses a slightly different notation for the LDA model. So as long as you know that there should be some continuous variable which talks about the topic mixture, there should be another continuous variable that talks about the word distribution. And then there should be some, Dirichlet quantity that affects the first one, another Dirichlet quantity that affects the second one. And then in between are the topic variables and the word variables. That's what you need. And people wind up giving random names to these things, unfortunately. I can't help it. I mean, especially since I was culling slides from different places, that there is this issue anyway that you are also looking at. But so here is, again, another version of the Dirichlet model, LDA, okay? Now, what happens is when you just unroll, you get something like this. Notice that this looks pretty much like that. Okay, that's basically what I'm talking about here. So if you just unroll, you get this, and you can do Markov chain Monte Carlo on this. I just told you. The Markov blanket for each of these are essentially your z's. They call them q's. The Markov blanket for z would be the theta and w, and the w is other pair, right? That was fine, except you want to get rid of the theta, which is pi here. And if I remove these nodes, then I get a network which looks like that, essentially. Okay, and that network essentially is saying alpha is now affecting all these, of course, directly, because they are no longer mediating this. This is directly affecting this. And furthermore, these guys all get, now remember that I also got rid of beta now. I got rid of both theta and beta, both the continuous quantities. And because I got rid of both theta and beta, I essentially now have only alpha and gamma, which are the Dirichlet parameters, which I have reset, which I set in the beginning. And then a much simpler network in terms of the variables, much worse network in terms of the sparsity. Because every z is now connected to every other z now. Okay, so now if you are trying to do Markov, Markov chain Monte Carlo now, essentially you would need to, if you are trying to resample this guy, you would need to resample this given the word, of course, and also all the other topics. Previously, you didn't have to do that because that would get taken care of at the theta level. But now theta is done, yes.
So when you remove the I and add an edge between Q and alpha directly, so that in turn introduces a dependency between all Qs. So why do we want to add an edge between Qs?
Oh, because you also removed betas. I think this is just a graphical interpretation here. There is no simple way of talking about just removing the edges. No. There is a modelization going on here when you remove a node. I mean, as to how you go from here to here, I didn't tell you enough about the graphical approach to make sense. Okay. All I am telling you is that the step that gets done in collapsed Gibbs sampling has some advantages, some disadvantages. Okay. From the structural point of view, it's quite disadvantageous. It has much less sparse structure. But from the inference point of view, Gibbs samplers are much simpler than this. Okay? Actually, this picture is not even shown anywhere in the parameter, the one that in the okay, this parameter estimation for text analysis. That's the Bible. If you want to actually rederive these yourself. Okay, and there it doesn't even look at the picture. Remember that Markov chain Monte Carlo can be done even if you don't know anything. I mean, even if you don't want to exploit anything about the network structure. Because all a Gibbs sampler asks you to do is resample one node given every other node's current status. Okay. And clearly, after you removed theta and beta, everything else, okay, after you removed theta and beta, essentially, you could still have talked about, resampling this node given all the words and all the keywords. All I am saying is actually, you don't need to worry about the rest of the words, only the word under U matters, because that's the base network part. And then these are correlated, so you actually have to take them into account. Okay, and in that particular analysis, they don't actually even show the network structure. They just directly use the base. Okay. So now, given that, so now I'm basically going to do Gibbs sampling on this. Okay. What that means is I'll start with all the words here, and then give some topic distribution up front, and then keep resampling the topic distribution, each topic one at a time. Okay, and to do that, the good part, there's a good part and there's a bad part. The good part is that for resampling a particular Zi, okay, that's trying to compute, you basically, suppose you're trying to resample Zi, which is one of these topic variables corresponding to the Wi word. Okay, maybe previously I gave 15 as the topic number for that word. Okay, now I want to resample it because based on the other guy's values, what is the most likely value for this? Okay, to do that, I essentially need to compute what is the probability Zi equal to topic number j given everything else. Everything else really would have meant all the Z's, all the WI's, and all the documents. The good part is the rest of the WI's don't matter, only that the W that you are connected to matters. For the Z's, every other Z matters because of that structure. Okay, so you need to compute this, and to do this, essentially, the derivation is shown in that other paper that I showed you. But eventually, what you will get, the good part as to why LDA caught on a lot of interest is, in fact, the sampler itself is quite simple. Okay, this sort of like NIBase. When you saw for the complete database network learning itself is very simple. Showing that what you're doing is right required understanding of maximum likelihood estimation. Okay, maximizing the likelihood. So the way you compute this posterior essentially is it essentially has just two numbers, and which is with respect to the current state of the network. And you compute the fraction of times the word WI occurs in topic J, and the fraction of times topic J occurs in document I. To do this, really all you need to do from a practical perspective is you just need to keep track of two documents, two matrices. One is a word topic matrix, the other is a document topic matrix. And these have counts. Okay, how many times is a word occurring under this topic? How many times this topic occurring in this document? And those counts can be just looked at by the current state of the network. Okay, and then the one tricky part is actually that you would think that the CWD, WJ, you would think would contain the number of times the word W occurs under topic J. Almost. It is almost true, except you don't count, in doing this counting, you don't count whether or not this word occurs under the topic that's currently being resampled. Okay? So that's basically not including the current instance, the instance that's being resampled right now. So from the point of view of the actual sampling, life is quite simple, because in fact these are all count matrices and they can be kept. You can keep track of them, and what you would get here essentially, notice that these are unnormalized, because let's say if there are 5 topics, you would get Zi equal to 1, a number proportional to k times 15, Zi equal to 2, k times 25, Zi equal to 3, k times 49, etc. Then to actually get the probability, you just normalize it. Right? You take k times 15 divided by the sum of all the other guys. That will get you into the probability distribution. And then use that distribution to actually resample Zi. That will give you a new state of the network. From there you get the next state. From there you get the next state. So underneath it, what's happening in the program, that the little program you ran, is you are traversing essentially in a chain of copies of this network. You start, let's say, with a copy of instantiated copies of this network. So instantiated copy is where you actually give the values also to the hidden variables, because you didn't observe them. The observed ones will already have their values. The hidden ones you basically initialize, let's say, and then let's say you resample this, you get an entire copy of this network with a different value for this. That's a new network. And from there you resample some other node again. From there you resample some other node again. So it's a chain whose states are the entire LDA network. That's what is happening under the hood. The good part is you never have to see this ugly network. All you needed to remember is these counts. To put that a little more in perspective, here is an example. Here is an example. So here is a case, and this paper also has an example. but it doesn't have as step-by-step example. This one has a little bit more step-by-step. Although given my timing, I'm not sure how much step-by-step I'll get to. Okay, but so here you have 50 words total spread over 5 documents. So each document, notice that documents can be 1, 2, etc. up to 5. So the first document has 10 words, second document another 10, third document another 10, all the way up to fifth document. So the total of 50 words, the total of 5 documents, and I'm trying to fit. Remember, I decide in LDA, I decide how many topics I'm going to fit. So I'm trying to fit 2 topics. Okay, so to give the entire state of the network, now obviously I know these are the WS. The entire network has only 2 kinds of nodes in the collapsed Gibbs sampling, right? Because the alpha and beta are given upfront. You decided what the alpha and beta are. And those are the ones that you do taking into account the sparsity. So for example, if alpha is less than 1, you get sparse mixtures of topics for the documents. And one thing that this guy points out is he basically says that alpha, actually there is a thumb rule that they give. Many people use this. I believe alpha equal to 50 by number of topics. Okay, and beta equal to some 0.03. And he says that works. People have actually tried, looking for the right fit and so on. We talked about this last class. Okay. But so there's an alpha and there's a beta. You can start with some values. The only network configuration is the W's, which always remain the same. Notice that in every configuration of your Markov chain, the observed nodes will have their values. You don't get to reimagine the evidence. Evidence is what it is. What you get to reimagine is what might be causing this word. So just as I said earlier, if there is like a river type topic and a finance type topic, and there's a word bank, sometimes you might be thinking the finance topic caused the bank. Some other times you might be thinking the river topic caused the bank. Eventually, when you stabilize, you need to really know which one caused this word. Okay? So anyway, so basically I have these words. The only other thing I need is the ZI values. The document numbers are known also because the words are from individual documents. Okay? The only thing I need is the ZIs. So in the iteration 1, I need to make up ZIs. So I just put randomly. Okay, I just said, okay, for this I'll say 2, 2, 1, 2, 1, 2, 2, blah, blah. I just made up. I just, randomly gave some value for each of them. It has to be, one of the 2 numbers, 1 and 2, because there are only 2 topics I'm considering. Just initialization. Now what I need to do is I need to compute the next network. Even though I said I will just resample just one guy, typically the way you would do is you would resample all the ZIs one after other. Then you will get an entirely new resampled network. That would be considered like a one macro iteration. You see what I'm saying? A micro iteration is just resampling one network, one ZI, then if you resample all the ZIs, you get one entirely new network where everybody has been touched once. This should make people start, thinking of the connections with the sweeping and prioritize sweeping in MDPs. Okay, if you do if you resample everybody once all the way, and then again resample everybody once all the way, that is like updating every state's value once before you update every state's value again. In prioritized sampling, you just basically, some states are sampled more often than others. And that's actually allowed for MCMC too. But it's easier to think this way for right now. Okay. So now the interesting thing, of course, is that I'm going to restart resampling. So I want to actually sample this value now. Remember that if I'm only resampling this, then everybody else has these values, and the words will, of course, have the word values. Okay? So I need to resample what ZI equal to 1, given all these guys and given all these words. And also ZI equal to 2, given all these topics and all these words. And then get that distribution from that sample, the ZI's new value. To do that, I will actually use, that's when I will use these counts. Now, if I want this number, what is this saying? This is Wj. The number of times the ith word is occurring in the jth topic. So I'm about to compute zi equal to 1. To do that, I need to consider how many times mathematics occurred in topic 1. But I should not be counting this instance. If I don't count this instance, mathematics occurred in topic 1 here, mathematics occurred in topic 1 here. So 2 is the number. What?
1 and 2.
What? No, all I'm saying is that I need to count here the word, how many times the word mathematics, because the mathematics is the ith word, occurred in topic 1, because I'm trying to compute what's the likelihood that zi equal to 1.
So the ninth one doesn't get considered because the zi is relative to.
Oh, yeah, sorry, you're right. I'm sorry. That's what you meant. Okay, that's correct. I'm just looking at di. Okay. So mathematics is in topic 1 here, but mathematics is in topic 2 here, so that won't count. So the count is 1. So all I'm saying is each of those numbers then can be computed just from this information. That's what the count matrices were keeping track of. Okay, now the other question, by the way, is, I don't know if you noticed, even I want to go back and show you, I don't know if you noticed, there is this beta and there is this w times beta. This is how, if you have not seen a word under the topic, normally it should be 0. But it will never be 0 now, because you will always have a beta in the numerator and w times beta in the denominator. This looks an awful lot like Laplacian smoothing. But we talked about the fact that what basically, so there are obvious connections here. Okay, what actually happens here is that expected value of the Dirichlet distribution would wind up corresponding to Laplace smoothing. That's what we did when we did the coin toss experiment. Okay, so the Laplace smoothing, etc., give you point estimates. They'll give you the exact value for the hidden variable. Bayesians don't want an exact value because there is no such thing as exact value. They want the distribution. If you take the mean of the distribution, you lost the distribution. If I have the distribution, I can get you mean, the variance, anything else you want, I can get you. That's what Bayesians do. Okay, so really, what you see as Laplacian smoothing essentially just winds up being the expected value of a Dirichlet distribution. But it's kind of nice to know that essentially the beta and the betas and alphas that you started with take part in these ratios. You can think of these ratios as the smooth ratios, but really, the reason they actually come out is, okay, let me just, I'll tell you that in a minute. But so I used that to resample Zi and imagine that Zi got 2 as the value. So now the current state of, now I want to resample, Z2. When I'm resampling Z2, what are the rest of the Zi's? All the shaded ones. Because this guy is no longer correct. See what this guy is? Yeah, this guy is no longer correct. This is the correct value. It just so happens that it's the same value. Okay, and then these guys were still the current ones. So using these, I resample this missing Z2. And imagine that that became 1. Now the new state is this, and of course the words. Do you see what I'm saying? Okay, now do you guys notice something? Which is that as we are going along, the counts can change. Right? Because the number of times, the topic is 1 is now being given to more or less words now. And word proportion in the topic can change. So you have to dynamically maintain these counts. It's not one single count matrix. And it's the final count matrix that will have very useful information. Okay. So anyway, so I keep doing this. Blah, blah, blah. I'm sorry. Okay. Okay. So up to here, let's say, and if I'm resampling this, I use all this and all this as the current values, and of course these are the current values, and I resample just this guy. Okay. And finally, when I did that, so when I resampled all the way here, I got, like, let's say, entire network. Everybody got a chance to be resampled. This is like a synchronous resampling of all the ZIs, just like synchronous value iteration. Okay. At this point, I can say I have done like one big iteration. And one more, until I think I have burned in. Now, when do you know that you have burned in? In value iteration, it was obvious. You know, the issue of when did a Markov chain burn in is a whole entire topic. Okay, and in fact, there are, you know, I don't even want to go into it, given that I have less than 3 minutes. Okay, but essentially, you know, people just, you know, I think this paper actually says that they use sometimes they use basically the known, you know, if they might know before they went to these topics and these documents, they might know that there are certain topics that do exist and there are certain words that do exist in those topics. And they might try to look at the current configuration to see if they agree with their intuitions. Do you see what I'm saying? If you happen to know that the bank is either a river topic or a, you know, finance topic, and this guy is putting bank as a part of something that looks like reinforcement learning topic, then you say, I don't like it, presumably. Okay, that's like a practical idea. Okay, now having done this, so R, just give yourself 1,000 iterations, k number of iterations, and at the end of k number of iterations, just, you know, raise your hand and say, I'm done. Okay, at that point, when you're done, what you have essentially, you can say that the final configuration is one configuration. And if I give you that configuration, you can then actually answer all the questions I have. You can answer which word came from what topic, for example, or how many topics, what is the topic mix in each of the documents. To put that in perspective, actually, if I just am giving you this, the final one, then from there, I can actually, from Z equivalent W, I can estimate the phi and theta, which are the topic mixtures and the word topic mixtures, so the document topic mixtures and the word topic distributions. Using essentially the same exact count matrices, except these count matrices have changed over the iterations. Right? And this one is just the probability of ith word being in the jth topic. How do I do it? I just look at, you know, how many times ith word is occurring in the jth topic. Notice that the ith word, let's say the second word is mathematics, but so is the 9th word mathematics. Okay, so how many times is mathematics occurring in topic 1 is what I might be asking. Divided by the total number of words that are occurring in topic 1, which would be the proportion of mathematics in topic 1. Right? So using that, I can get basically the topic, you know, the word topic distributions, and similarly, I can get topic document distributions. Because again, I have the information. If I just have this, I do have the documents. I know how many times topic 1 occurred in document 1, how many times topic 2 occurred in document 1. I can compute this. Okay, so that's basically the end of the magic, right? And now you have the phi and W, and phi and theta. Okay, and that's what we were showing. Using that, you can do, you can show these are the topics, and this is the, you know, for each topic you can then show the top k words, the ones with the highest probability, for example. Okay, and the last thing that I would not obviously go into is that essentially I have sent a mail to the, so the thing that obviously I glossed over here, like majorly, is how did I come up with this formula? How did you come up with this formula? Okay, not this formula, actually the important one is the Gibbs sample formula. Okay, And to do that, essentially the best way, if you are interested, please read that paper, especially in section 5. And I also tried to send you an email giving sort of an annotated way to follow that paper if you are interested. The one thing I would tell you though, which is that eventually you do know that gammas exist in the Dirichlet distribution. That much you know. Nothing else you know gammas exist in the Dirichlet distribution. And then most of these things that when you're trying to estimate this, you will wind up getting something as ratios of gamma functions. In the end, however, there is no gamma left. What happened to the gammas? Gamma is nothing but factorial function for continuous variables. Remember we said that. So if I told you gamma n plus 1 on the top and gamma n in the bottom, then I just have n plus 1. That's how gammas go away. I mean, that basically just tells you that there is not too much magic going on between this and that if you take time to actually look at why things are getting cancelled. As to why gammas come, those wind up basically, those are the normalization factors in the Dirichlet distribution. Okay, and the Dirichlet integral values depend on the gamma functions. Okay. So I think it's beyond 4:15, so I will have to stop here. Actually, I think let me show you this one little thing that in the other paper, the Pina's paper, they show, for example, suppose they had actually started with these topics. This is another. This example actually also tells you that this has nothing really to do with words. It can be on any kind of a data. This thing looks like images. Imagine that I have, these are the topics. So my topics are a rectangular band here, a rectangular band here, a horizontal band here, a horizontal band here, etc. And I will generate new images by basically combining these topics. That's my generative model. Okay, so then they actually generate these images by combining them. And then they give it to this Gibbs sampler to try and see if it can actually reconstruct this is the ground truth. This is one of the few cases where you know the topics because you mix them. Did you actually get back to the old topics? And so they show this picture, nice picture, where they show you at every different iterations, at the 100th iteration, 200th iteration, up to 500th iteration. Okay, they're showing what is at that time, what was the topic looking like? What is the estimate of topic looking like? It's pretty impressive. Right, in the beginning, obviously they have no clue, but slowly they critically converge to the right topics. So they reconstructed it just from the data. As long as the data was originally generated from these topic mixtures. Of course, the problem that you normally have is you have no clue which topics generated these documents. And if in fact there are some set of topics that did generate this document, even that is not clear. So when you have a bunch of points and you're trying to fit a line to it, you have no actual clue as to whether somebody actually had a linear process and there was some noise attached, so you got a slightly curvy set of points. You just assume that let's hope that, and if that is the case, what's the best line? And that's what this model did. Yes?
If we did it with 8 topics.
Mm-hmm.
So if I had decreased it to 6.
That's a good question. There is no guarantee. So in this case, is the only place where you could have reconstructed the reality. So did you reconstruct it? You did. You did. But if you did anything more, if you had 10 topics, what happens to the other 2 topics? All bets are off. If you have 4 topics, what happens to them? All bets are off. Okay, so I'll stop here, and we will have the final exam on next Wednesday in the same room. But the time is different. Okay.